We're going to move on to Oleg Kovalevskiy. Sorry if I've mispronounced your name. He's a protein biochemist, later turned to the computational side and methods development for macromolecular crystallography. And he spent 5 years working with Gary Murshidov's on refinement at Lowresolution, and has moved to CCP4 core team developing automation solutions like CCP4 Cloud workflows and low resolution structure refinement pipeline, which he'll tell us about in his talk. Oleg, please.
Yes, I have a pre-recorded video to keep time on track, so we can start with it, and then I can answer questions.
Thank you.
Colleagues,
so can you make the video live?
Today I would like to speak about refinement at low resolution and about automation of refinement. So, what is the problem with refinement at low resolution? Mathematically speaking, the problem is poor observation to parameter ratio. I'll illustrate this with a simple example, thanks to Rob for the slides. Imagine we need to fit a line into several experimental points. Points here are analog of X-ray reflections, and fitted line is like a protein structure. To fit a line, we are fitting two parameters of the equation, A and B. Could we fit two parameters with 5 observations? Yes, we can. And the line will be relatively stable. If we move one of the points, the line will remain nearly in place. Can we fit a line with just 2 observations? Yes, we still can, but line is sensitive to changes in observations. If we move one point, line will shift substantially. Well, can we fit a line with just 1 observed point? We can fit infinite number of lines, meaning we can't fit one line. This is called ill-posed problem because there is no unique solution. Exactly the same thing happened with X-ray structure refinement. Now let me show you how this works in crystallography. Let us consider a particular structure solved at 1 angstrom resolution. Number of reflections for this data set is around 100,000. We can roughly, as a simplification, think this is our number of observations. Well, in reality, not all reflections contribute equally due to different measurement errors, etc. And we speak about unique symmetry-independent reflections. So 100,000 observations. And we have 2,300 non-hydrogen atoms. So we have 44 reflections observations per 1 atom. How many parameters per atom do we refine? As we consider atom like a point or a ball, we describe its position with 3 coordinates, x, y, z, making 3 positional parameters. Plus, we describe positional uncertainty via B factors. If we refine this uncertainty anisotropically, we need 6 parameters. 3 plus 6 equals 9 refined parameters per atom. 44 reflections or observations per atom. This gives us observation to parameter ratio of roughly 5. Can we do refinement with such ratio? Yes, we can, and we do. Let's make things worse. Average resolution of the structure in the PDB is about 1.9 angstrom. What if we cut resolution of our data to this? We will have only 15,000 reflections left for the same number of atoms. That means less than 7 reflections per atom. Can we refine 9 parameters per atom? No, we just can't. The trick is we can switch from anisotropic B factors modeling to isotropic. So it will be 1 uncertainty parameter per atom plus 3 positional parameters gives 4 parameters per atom. Observation to parameter ratio will be just 1.7. Not good at all. It means at 1.9 angstrom we already can't refine positions of atoms independently, and we need chemical restraints to improve the ratio and keep refinement stable. Let's now get to really low resolution, like 3.5 angstrom. We will have only 2,600 reflections. This is really like 1 reflection per atom. And we need to refine 3 positional coordinates. Sounds like this is impossible at all. But there are a few tricks. Look at this tyrosine side chain. It has 8 atoms. Let us consider these 8 atoms as one rigid body, which means we constrain all bond length, angles, polarity, etc. To describe 3-dimensional position of any rigid body, we need just 6 parameters. 3 translations, 3 rotations. That means we need to refine just 6 parameters per group of 8 atoms. So we refine less than 1 parameter per atom. Sounds much better, but actually tyrosine side chain is not floating in the solvent. It's quite connected to the main chain. That means we can describe position of this rigid body tyrosine side chain with just 2 parameters of 2 torsion angles. And these are 2 parameters per group of 8 atoms. If we refine just 1/4 of parameter per observation, that gives us quite reasonable observation to parameter ratio, isn't it? That's what we do at low resolution, applying as many restraints derived from our prior knowledge as possible. Restraints sort of link atoms together, so we refine parameters not for a single atom, but rather for the groups of atoms, allowing some degree of flexibility, of course. This is how we improve observation to parameter ratio. At medium resolution, following restraints are automatically applied. Restraints on bond length, angles, chirals, planes, torsion angles, and van der Waals repulsion. As resolution goes lower, we can start applying more and more additional restraints that are based on our prior knowledge. Restraints on B-values, and CS restraints on crystallographic symmetry. If we have several identical protein chains in the symmetric unit, we may keep their conformation similar and use these as restraint. Jelly body restraints, hydrogen bond and secondary structure restraints, restraints to homologous structures, and nucleic acid restraints, base pair and base stacking. So, how do you technically apply these restraints? For B-value and CS and jelly body restraints, you only need to specify refmark parameters to switch them on, and refmark will do the job. For hydrogen bonds and restraints from homologues, Prosmart program can analyze your structure and homologous structures and generate and write out set of restraints that will be used by refmark during refinement. Lowresolution is automated pipeline that wraps Prosmart and refmark to help users with refinement at low resolution. For nucleic acid, there is also a specific tool to generate restraints aiming at idealization of your target nucleic acid structure. Later, these restraints could be used by refmark. So, Prosmart program by Rob Nichols is really a Swiss Army knife, as it can be used not only to generate external restraints, but also for detailed analysis of homologous structures, to accurately superpose structures, find local similarities, identify rigid domains, etc. It can generate restraints based on homologous structures supplied by user and hydrogen bonds and secondary structure elements. What external restraints are doing? Imagine structure of your target protein. It has distance d between those atoms. And also you have high resolution homologues that have distance r between the analogous atoms. Prosmart would accurately superpose those structures, identify corresponding atom pairs, and write out distance r from high resolution homologue as target restraint. Then you will run refmark and give these external restraints to it. So it will use distance r as a target for mathematically sophisticated regularized refinement of the distance d. And believe me, quite often it is doing magic for refinement at low resolution. How do we do this practically? This is easy. In CCP4 interface, external restraints is just part of refmark interface, section called restraints. You just need to specify reference model. You may adjust Prosmart parameters, but defaults usually working well enough, and press run button to start refinement. Interface will run Prosmart first, and then refmark will use these restraints to improve your structure. In CCP4 Cloud, it's essentially the same. Once you specify homologous model in refmark task, you will have parameters for external restraints, very easy to run. However, to achieve best possible performance, you will need to play with parameters and also find optimal homologue for generation of restraints, which may result in a lot of manual work, especially if you have many homologues available. Low resolution structure refinement pipeline, Lowresolution, has been designed to be completely automated tool to assist refinement at low resolution. You even don't need to supply homologues. The pipeline will find them and download automatically. It will carefully analyze your structure for twinning, figure out best scaling and solvent parameters. It will smartly generate and run several refinement protocols. Then it will assess the results for both geometrical quality and their factors and return best result. Again, this is a very simple interface. You just need input files and make sure that auto search for homologues is on. And CCP4 Cloud interface is essentially the same. Minimal number of parameters, maximum automation. Okay, let's speak about something interesting. As you know, recently a real revolution has happened in the field of structural biology. I mean, outstanding performance demonstrated by AlphaFold during the latest CASP competition. This was really a breakthrough in protein modeling, and I believe tomorrow will be several talks about this. As you may know, DeepMind, together with EBI, has started an amazing project, massive modeling of the protein structures from key organisms. Currently, 300,000 of pre-calculated models are available, and about 1 million of the models will be released in the future. I had a specific question. Are these models useful as a source of external restraints to improve refinement? From theoretical point of view, interatomic distances in AlphaFold models are derived from a bunch of homologues, and therefore they should have biological meaning. So I have tested Lowresolution on 59 low-resolution structures. If you just run current Lowresolution version that will download homologues from PDB databank and use them as source of external restraints, Lowresolution will improve geometry and R factors for 56 out of 59 examples. If instead Lowresolution will use BI database of these AlphaFold models to search for homologues, it will improve 44 examples. This means AlphaFold models are often good enough to contribute positively to the refinement, and that's great finding. But I need to say that 22 out of these 44 structures using PDB database showed superior performance, even better geometry and lower R factors. But this also means that for 22 out of 59 structures, external restraints generated from AlphaFold models outperform those from PDB experimental structures. Okay, here we have 50-50 situation, and the next question is, what if we use both databases simultaneously and mix experimental structures from the PDB with AlphaFold models? Yes, that's worked quite well. Only 3 examples could not be improved as before. For 16 examples, this mixed mode performed better than PDB-only mode. By performance, I mean improvement of both geometrical quality and R factors. For 27 examples, mixed mode showed similar performance to the PDB-only mode. There are a few examples for which PDB-only or AlphaFold-only modes produced better results, but it's relatively few of them. For a vast majority of the examples, this mixed mode could be recommended, and I will make it default option for the next Lowresolution version then. This new version of Lowresolution will be released in CCP4 so I look forward to it. Okay, let us speak about something else. Quite often students ask why there are that many parameters of refinement, why there is no single refinement protocol. The answer is model describes your data, and different data is described differently. For instance, at high resolution, we model anisotropic B factors, and at very low resolution, we may opt for overall B factors. Apart from that, we have different stages of refinement. After molecular replacement solution, majority of the atoms will not sit in their right places, and we need to move them first. Also, there could be missing parts of the structure. So only later, when 100% of residues are built and put in place, we can do fine-tuning, like anisotropic B factors modeling. This could be confusing for novice users. Can we help somehow? Yes. We have introduced automated user advice system called Verdict into CCP4 Cloud, and it is currently ported in CCP4 2. Practically, Verdict is a part of task report. It appears after refmac run, and Verdict analyzes quality of the output structure and provides clear text explanations on what is suboptimal currently and could be further improved. Verdict takes into account many considerations like resolution of the data, stage of the refinement, etc. So its suggestions are usually quite meaningful. It does not only tell you what's wrong, it also suggests which parameters of refmac could be changed to improve refinement. It's communicated in the text, but also we have this clone job with suggested parameters button. If you press it, quite naturally RefMac task will be cloned, and instead of default values, it will be filled with suggested values, highlighted in blue. User still has full control and can modify these suggested parameters. Then you can hit Run button and enjoy much better refinement results. If results are good, verdict may not have any suggestions anymore, and that button clone with suggestions disappear. I hope this analysis of the refinement runs by verdict will be useful and educational, not only for novice users, but also could save time for busy industrial users, for instance. Speaking about saving time, in CCP4 Cloud, we have introduced new concept for the automation at the project level, so-called workflows. There are workflows that can help you to solve the structure with experimental phasing or molecular replacement. Another useful workflow is for refinement and ligand fitting. It can automatically fit ligand, but without ligand, it will just run a series of RefMac jobs with parameters suggested by verdict. It will run RefMac until convergence, I mean, until verdict is happy and don't have suggestions anymore. So this is automation of refinement that works across all resolutions. Please give it a try. And that's all. I would like to thank all the people who contributed to this work, especially Gary Pandrop and my colleagues from CCP4 core team, Charles, Eugene, Andrei, Ronan, David, Will, and Kyle. And thank you for your attention.
Thank you very much, Oleg. Really interesting analysis and useful tools. We're running a bit late, so I'm just going to have two quick questions. One is from Gustavo Lima, and he asks if you can run verdict outside the CCP4 interface using a command line.
I think no, you can't at the moment. It's implemented in Python, so it recently have been mostly imported into I2, but unfortunately no. I think it can be called as a Python function, but it's not that straightforward. We actually might think about making this available as command line tool if you're interested.
Okay. There's a question on, did you account for predicted local model quality of the AlphaFold models that you used in Lowresolution?
No.
No. Okay.
So I just took models as they are. So yeah, there is room for improvement. I just recently started playing with that, and results are quite encouraging. So yeah.
There's a couple of questions about using of AlphaFold. So Sebastian was asking if you can imagine turning this around and include consistency with low resolution X-ray data into AlphaFold. And then Isabel is asking whether you are using restraints derived from the identical structure in AlphaFold. So are you using just one model or more than one?
So about the first question, I am not sure. Well, obviously AlphaFold modeling is based on neural network, so I don't see how these restraints could be applied there. It's completely different technology, but they sort of derive distances from homologous structure. That's what they do for modeling, but it's totally different setting. Speaking about second question, what was it?
So do you use the restraints derived from identical structures in AlphaFold?
That's the thing. So in some cases, so let's say what Lowresolution is doing, it is running a number of protocols and checking which one works best. And in these protocols, it tries single homologues as well as mixture of several homologues, because RefMac can handle more than one distance restraint for a particular bond. So in this mixed mode, AlphaFold models perform nicely, and they can be effectively mixed with experimental models, which is also a nice finding.
Thank you very much, Oleg. In the interest of time, I'm just going to move quickly to our third speaker,